In the last section, we ended the lecture by asking ourselves, how can we convert our perceptron, a binary classifier, into a multi-class classifier? Two popular techniques for doing this are one versus rest and one versus one. The idea behind one versus rest is, suppose you have 4 target classes, A, B, C, and D. Then you train 4 binary classifiers, A versus not A, B versus not B, C versus not C, and D versus not D. Given a new sample X, you have each classifier make a prediction about X. So ideally, each classifier outputs some sort of score, like a probability, and then you just pick the one with the highest score. With one versus one, you'd train 6 binary classifiers, one for each pair of classes. Given a new sample X, have each of them make a prediction, and then let them vote on the most likely target class. Of course, it's possible to have ties, so it requires a tie-breaking mechanism, which usually means it requires some sort of score function, just like one versus rest. So, how could we implement a one versus rest system for our perceptron? Take a look at this dataset and separating line. Hopefully, it's intuitive that the distance between a point and the line coincides with how confident we can be about the model's prediction. So, given some point x, the score we should give it is its distance to the hyperplane. And ideally, that means we should use the hyperplane with maximum margin between the two classes, i.e. the one found by support vector machine, but we'll settle for whatever hyperplane the perceptron gives us. So, see if you can implement a one versus rest system to turn our perceptron into a multi-class classifier. Here's the code I came up with. So, before I was using a lowercase w to store a 1D array of weights. Here I use a capital W to store a 2D array of weights, where the kth column of the array represents the weights for the model that predicts class K versus not class K. In other words, each column of the array represents a different perceptron. With that modification in place, my fit method is pretty self-explanatory. It's basically the same as it was before. I just have an extra loop that iterates over each target class, finding the best weight vector for the model, class K versus not class K. Now, there is a significant change to the predict method. For each test sample X, we need each perceptron to tell us the distance between X and the hyperplane. So, given some weight vector W and a new sample X star, how do we determine the distance between X star and the hyperplane defined by W? Well, the shortest distance between the hyperplane and X star is going to be given by a vector V, perpendicular to the hyperplane that touches the head of X star. So our goal is to find the norm of V. And let's define XP as X star minus V. Well, we know W.XP equals 0, which means W.X star minus V also equals 0. At this point, recognize that since V and W are both perpendicular to the hyperplane, V is just a scaled version of W. In other words, there's some constant alpha such that V equals alpha times W. So we can restate the previous equation as W.X star minus alpha times W equals 0, which we can rewrite as W.X star minus alpha times W.W equals 0, which we can rewrite as W.X star equals alpha times W.W. And the only thing we don't know in this equation is alpha, so let's solve for alpha. We get alpha equals W.X star divided by W.W, which is the same thing as W.X star divided by the norm of W squared. So we want to find the norm of V. Well, the norm of V equals the absolute value of alpha times the norm of W. Plugging in our definition for alpha, we get the norm of V equals the absolute value of W.X star divided by the norm of W. Getting back to the predict method, once we set up X1, we calculate the distance of each point to the hyperplane for each class, except we don't just calculate the distance, we calculate signed distance. And this is important. If we only knew the distance between a point in the hyperplane, it wouldn't tell us if the model is voting for or against a certain class label. So we need signed distances to keep track of which models are leaning for or against each class label. So signed dists is a in-row by k-column array of positive and negative distances. And then for each row in signed dists, we determine the column with the largest value because that's going to be the most confident prediction for a particular class label. Lastly, we look up the class corresponding to that column index. Let's give this puppy a whirl on the MNIST dataset. With max updates set to just 100, we're able to achieve 85% accuracy. When I let this thing train with max updates set to 1000, it actually gets 89% accuracy. Not bad, considering we're using mere hyperplanes. By the way, if this is the first image classification model you've coded from scratch, go ahead and pat yourself on the back. Getting to this point is a pretty cool achievement.